she's शी इज बिजी राइट अच्छा शेयर अब कोई आया है हमारी मीटिंग में कि नहीं बताया आपने उनको तहरीम आ गई है ठीक है और एमन को भी कह दो कि पहले वाले लिंक से ज्वाइन करें मैंने ग्रुप में ही कह दिया चलो जी यस डस्टर एंड अ पॉइंटर ओके चलें अब आप स्टार्ट कर देना ठीक है माइक भी दे दूं तुम्हें अच्छा अब किसी तार पे पाँव नहीं रखना डोंट यस बिकॉज इफ एनीथिंग मूव्स इट विल डिस्टर्ब राइट स्पीक लाउडली एंड आई थिंक वी कैन हियर इट चलें स्टार्ट
Good afternoon, everyone. My name is Asad, and this is my final presentation for Physics 422 Nuclear Physics. The topic of my presentation is, although a topic that might seem a little boring, that is alpha decay only, but I have turned it into a fancy term that says that alpha decay as an application of quantum tunneling, theoretical proof of Liebman-Nuttall's law using Gambo's theory. Now, what is alpha decay? In order to dig into the details, we will have to look into the superficial knowledge first. And alpha decay is kind of a nuclear reaction, a spontaneous nuclear reaction, in which a large-sized nuclei disintegrates into a daughter nuclei while emitting a particle that scientists at first termed as alpha particles. Those alpha particles later on turned out to be regular helium nuclei. They have very low penetrating power and they can ionize their surroundings to a great extent. They can be shielded by just one thin piece of paper. In fact, the strongest kind of an alpha particle that has ever been found was found in perhaps 1930s, and it penetrated up to 23 centimeters in air. Scientists were dazzled, and they were like, what kind of alpha particle is that? Rutherford, the person who did most of his initial work that led to nuclear physics, used alpha particles, and even he was dazzled. So he later on realized that alpha particles are not the only kind of particles that are decayed in that manner. And that was actually a hydrogen nuclei. Okay, now we get it that whenever a nucleus gets fat enough, it spews something out. But why? Why is that so? Why does it need to spew something out? Like, was it not fine by itself? As it turns out to be, it was not. It was not fine by itself. You see that the general equation for that reaction is given over here. That says that if you have a particle, let's say a parent nuclei named X, and it has an atomic mass of A and an atomic number of Z. Now this particle will disintegrate into a daughter nuclei, and if it is a regular, conventional, orthodox alpha decay, the daughter nuclei will have an atomic mass 4 units less than its parent nuclei, and its atomic number 2 units less, resulting into an emission of a particle that at first we named as alpha particle. Later on, we found out that they are just helium nuclei, having their atomic mass 2, having their atomic number 2 and atomic mass 4. Well, these are some superficial things that you must know about alpha particles before diving into the detail. But why? Why? Why does it have to disintegrate? Like, this question always dazzled me. So I looked into the details and found out that your answer is really interesting. You see, our nucleus, if we look into a regular, let's say a Bohr atom, we see a nucleus in the center and electrons orbiting the nuclei in a definite orbit. Although this is not a correct description, like these are actually probability clouds, but for the sake of simplicity, I'm going to say that. The electrons are held in their orbits because of an electrostatic or electrodynamic force of attraction between your positively charged nuclei and your negatively charged electron. Okay, that makes sense because positive charges always attracts negative charges, and when we have same kind of charges, they repel each other. It makes total sense, and it should happen. But then again, we see that a nucleus is a very tight species. It's a very small body, so small that we actually count it, we actually measure it in the order of femtometers. It's ridiculously small. So how come those protons stay together, are glued together so tightly? Well, we looked into the detail of the nuclei, and after some rigorous mathematics and beautiful experiments, we found out that there are actually four forces of nature. One of them is strong nuclear force, and I will call it S and F. You see, the strong nuclear force is ridiculously strong. So strong that it can hold those positively charged protons all together. It doesn't matter how much they repel each other using their conventional Coulombic force. Strong nuclear force just overcomes it, as if it's an elephant and Coulombic force is an ant. Anywho, there is a downside of this particular force. It is very, very short range. So what? So what if it is short range? Nucleus is a short kind of a body, it is a small body, but it turns out to be, even though it is not a problem for regular sized nuclei, but when its mass exceeds the value of 190 AMU, it gets tricky. It gets a little tricky at that point because your strong nuclear force is very, very short range. And because of that, your Coulombic force start getting the better of it in the long run. So what happens is that your nucleus, let's say that this is your nuclei, we zoom it in, we zoom this thing in, and we find out that this is your nuclei. It spits an alpha particle out of it. Alpha particle out of it. It spits it out. Now people say, why alpha particle? Actually, alpha particle is a very stable kind of a nuclei. We have read the golden numbers of nuclei and it follows one of them. But yeah, it's not the only particle. As I explained earlier, they did observe a proton emitted out of it only. Yeah, so alpha particle can be emitted. In fact, it is the one that is being emitted most of the times. Now, why? Again, why? Well, you see, the alpha particle is actually emitted to achieve stability. And it makes sense. After it emits an alpha particle, its size is reduced. Its Coulombic force that was bugging that nucleus from the inside is not bothering it anymore. So yeah, that's great. It's great for me, works for me. But it turns out to be, there is this one slight little problem. There is this one teeny tiny bit of a problem. Do you know what's that? It's almost impossible for an alpha particle to decay out of its nuclei. Your regular laws of physics just do not allow it. For example, let's imagine that I, Asad, am jumping out. I'm trying to jump and trying to escape the field of gravity. Now, as far as my velocity will be less than the escape velocity of Earth, there is no chance that I would escape its gravitational field right now. It's impossible. But it still happens. Why? Then again, why? Well, because quantum physics. If something doesn't work, go quantum. Yeah. You see, imagine that we have this ball, and there is this energy barrier of height h. The energy that you are providing, the kinetic energy that you are providing this ball to, is less than, let's say, it's less than the height of this barrier. So no matter how many times you push it through the cliff, it'll always fall back and you'll never cross that hill, right now. But classically speaking, it is true. Quantum? No. Let's see why. You see, when you go quantum, the nature of particles, the nature of matter, the nature of reality itself changes into something very non-intuitive. Matter starts acting like a wave function to be more precise. And if you would look into the classical mechanics of waves, simple regular mechanics of wave, you do realize that whenever a wave hits a barrier, unlike a particle, it doesn't stop there at that very moment. It doesn't stop immediately. It decreases exponentially. Its amplitude decreases exponentially. And sometimes when the barrier is thin enough, it manages to take its little peak out of the barrier. And the name is very beautiful and self-explanatory. Evanescent wave. I love that name. Now, this is an evanescent wave that is being passed out of that barrier, despite this wave function having less energy than that of a barrier. And that's beautiful. But we have to see what those wave functions actually define. What do we mean by having a wave function, leaving a speck of it at the other side of the barrier? You see, that wave functions actually define the probability of us finding a particle in a given location under a certain potential. Now, if we're having a speck of wave function at this side of our graph, at this side of our potential, it means that there is a slight probability that we might just find this particle over here too, on observation. Before observation, it's everywhere. It's literally everywhere. In fact, everything is everywhere. Even I, being a macroscopic body, I am here, I am here, I am here, and there's an infinitesimal chance that I'm on the moon. And no scientist can negate that until he observes me. When they observe me, my wave function collapses. Anywho, but there is this transmission probability that denotes the probability of this particular wave function, and it can be get by solving your Schrodinger's wave equation quite orthodoxically, and we get this as transmission probability to be e to the power negative 2k2l, where L is the barrier width, like this width, and U is, and K2 denotes this thing, where U is the energy of the barrier, the height of the barrier, and E is the energy of the particle that is being passed out. And M is the mass of the particle moving out. Okay? All right. So what does that have to do with our nucleus? What does that have to do with our alpha particle? As it turns out to be, the nuclear diagram of an orthodox nucleus is just like that. But then there is a trick to it. No, we can see that the barrier's height is greater. Due to a resolution problem, I think that you might not be able to see what I wanted to show you all. But anywho, you see the particle. Oh crap, that's good.
You moved this wire.
Yeah.
You can, okay. Can you, is it?
It's still working, but Dudana, you might pause this video.
दुर्दाना अच्छा आप थका नहीं ना तबीयत ठीक है यस मैम
Hello.
अच्छा शर्जील ने भी ज्वाइन किया
Why so delicate?
अपने मैसेज से अपने
Why is everything so delicate?
बेटा that's we
How about I start explaining on the board?
We want them also to see, and you also want it recorded, and
It's fine, I can explain on the board.
it's okay. It will just take a minute or so.
I'm not familiar with that device.
नहीं इससे नहीं power button को करो. The blue one, the blue blinking button, उसको off करके on करो.
It's off now.
Okay.
Yeah.
हाँ. नहीं
Yeah. Why is everything so fragile? If it is not working, I do not have any. Oh, yeah, it's okay. It's working. It's saying something.
It's working. Okay. So the thing is, don't touch the wires.
Yes.
We have not yet invented a technology where we can work without wires.
Yeah, but yeah, we can make wires strong though.
No, we can of course improve this, but this is like not a permanent setup, you know.
Yes, ma'am. Okay, it's working again.
So now just be careful, okay?
Yes. So you may restart.
इसलिए ये कर लो, हाँ. शजील से कर.
Yeah, so if you were to look at this diagram,
Call कर.
you see that the energy of the alpha particle that is being emitted out of our nuclei is usually at the order of 4 to 9 megaelectron volts. But the energy barrier has the height of 20 to 24 megaelectron volts. So now this is analogous to the thing that I have just told earlier in the previous slide. But the nuclear potential diagram is really different from the one that we saw earlier. You see, the nuclear potential diagram that defined our transmission probability was kind of like this, where the height of your barrier was U, the length of the barrier was L, right now, and the energy of the particle that is trying to escape the barrier is E. All right? Now, there is a certain probability that it leaves an evanescent wave out of it, and that probability is T is equal to e to the power negative K2L. Makes sense, but does this thing that I just drew, does this look like that? No, it doesn't. So what should we do? We should go for maths, because maths is strong and we should use its strength. All right, so I will borrow some techniques from my good buddy Newton and his calculus. Now, you see, it's really easy. I just turn this curve that is being deteriorating as 1 by r linearly into small rectangles, infinitesimally small rectangles having their width equivalent to dr, and then add them all continuously between r and r naught, where r is the radius of the nuclei and r naught is the energy of the Coulombic force, is the point where the energy of the Coulombic force turns out to be equivalent to the energy of our escaping alpha particle. All right, makes sense, but how would we do that? Well, maths, of course. Well, you see that derivation, it's beautiful, it's amazing. And well, this is the, the nutshell kind of a thing of our derivation. At first we take, you see, at start our expression was this one. T is equal to e to the power negative 2kl. Now, we have integrated it. First of all, I have taken natural logarithm in order to avoid writing everything in exponents. It's very tedious. So we have taken a natural logarithm, and with this we get ln of t is equal to integral of r to r naught minus k2 into dr. What was k2? We have defined it earlier to be k2 is equivalent to square root of 2m into u minus e divided by h bar squared. Right now it was kind of like that. Yeah. Well, it is what it is, k2. We plug in that value and then we solve that integral. Now that integral is a little difficult to solve. In fact, when I solved it, I had to substitute its value 11 times to get the solution. Now, if you want me to do the derivation over here, I love maths, I love doing derivations, I can go for it, but it's up to you guys. So
I think you can go with the main equations and the explanation.
yeah, the main equations are written over here.
Yeah,
the
that's
derivation is beautiful. Doing them.
That's in the paper, right?
Yeah, that's in the paper, the one that I sent you.
Yeah, if you have a question, you can ask, okay?
Yeah, you can ask anytime, but that anytime will start once I end this.
Okay, so, yes, okay, so you can
Alright.
proceed, right?
Okay, but so at the end of the day, we get this thing. And although it's an exact equation, it tells you about the exact transmission probability in a general term, like no matter what kind of situation you have, you can explain it. You can explain that using this little formula. But only problem is that it's not little. It's big and tedious, and no one wants to memorize this thing. At least I won't. So we can do something, as Dr. Woodward always used to say, physics without approximations is almost impossible. If it makes your work easier, you can go as bizarre as pi is equal to e is equal to 3. Sue me if you don't like it. So what we do over here is that at first I would apply the binomial expansion by declaring that r is r naught is very, very less than r. And with this, my expression will shrink up a bit. And after that, I will substitute the value of r using this one clever trick, and it's beautiful and very classical in nature, not hi-fi as everything has been ever since I started speaking. We know that E is equal to 2 ZE square divided by 4 pi epsilon naught into R. Right now, everyone knows about it. But what I will do is, I will shift their places. And I will get R to be equal to 2 ZE square over 4 pi epsilon naught into, E. So rather than having the radius, the distance as a variable, rather than having that distance as a variable where your Coulombic potential is equivalent to the energy of an escaping alpha particle, it's very difficult to solve. Now that with that kind of a variable, we have a rather easier variable, that is E. And we know the energy of the escaping alpha particle. So we will plug that value into that expression after applying the binomial expansion. And we will get, and then by applying the values of all the constants that are present in that equation, we'll get this beautiful expression, this beautiful formula. Like, I'm in love with that formula. That states that natural logarithm of your transmission probability is equivalent to 1.29 into z power 1 by 2, r naught power 1 by 2, minus 1.72 ze power 1 by 2, where z is the atomic number of your nuclei, r naught is the radius of your nuclei, z is again your atomic number of your nuclei, and E is the energy of your escaping alpha particle. Now you see the similarity with the Eager-Nuttall's law? Well, that law was actually not devised mathematically, like taking your assumptions and doing the maths over it, just like orthodox theoretical physicists do. It was actually by meticulous experiments we found out that there is this particular trend that our nuclei follow while decaying using alpha decay. The only difference between them arises because over here I use natural logarithms, log with the base of E in my calculations, and they use log with the base of 10. And second of all is that mine use ideal conditions, ignoring the kind of attractive forces that arise along with the repulsion. So yeah, that teeny tiny bit of a difference is from that point. Anywho, this is very similar to Giegel-Friedel law, and it shows exponential decay as we always see in an alpha decay. So, what are the conclusions? There are three very basic, very interesting conclusions that I drew out from it. First one, radioactive alpha decay is only possible because of quantum tunneling. Second one, such process can never happen classically. Third one, whenever classical physics stops working, go quantum. And this is it. Thank you very much for listening to me. And if you have any questions, feel free to ask if you're not afraid of that person.
Who is this? Okay, good. That was nice. So, yes, questions? No, just nice. Okay. You? तुम बच्चे? No question? Come on, तुम quantum पढ़ रहे हो? Oh, ho. Achha. Okay, fine. Let's go back.
It doesn't apply on you though.
No, but why did you choose this?
It's a joke.
Okay. That's fine. Okay, go back.
Over here?
No, go further back. Okay. Okay, so can you give us some applications of alpha decay?
Oh yes, there are some very beautiful applications of alpha decay. I didn't choose to write it in my slide because there were already 10 slides, way
Yes,
too much.
that's
Yeah.
fine.
But applications, we wouldn't be alive if it were not for alpha decay.
Okay.
If it were not for alpha decay, the suns wouldn't shine. The sun or stars in the galaxy wouldn't shine.
Hmm.
Everything would have been cold. There would have been almost no nuclear fusion.
Okay, yes, that's quantum tunneling as
Yeah,
well.
quantum tunneling
Yeah.
and specifically alpha decay in quantum tunneling. And alpha decay is usually thought to be emission of alpha particles. However, if you go into details, it's just one of the types of alpha decay. And there are some more finer grades of it where helium-3 is released. Sometimes a deuterium is released. Sometimes a tritium is released.
The different isotopes of.
Yeah.
Okay.
So the reason was Coulombic repulsion gets the better of your strong nuclear force, and poof, it moves out of the nuclei.
Right. So what's the strong nuclear force?
Strong nuclear force is one of the four fundamental forces of nature that holds the atomic nuclei together. It is extremely strong. In fact, there was this number that while I was looking at a research paper that said that it is perhaps 10 to the power 5 times stronger than your electromagnetic force. Like ridiculously strong, but it is extremely short range. They exchange, you see, according to quantum field theory, every physical interaction that happens between two kind of particles, it happens by an exchange of a whole number spin particle. The whole number spin particle that is being exchanged in your strong nuclear force, it can be W and Z boson, and sometimes your pi mesons. The W and Z bosons are actually used while the strong nuclear force is acting between the quarks of your proton or neutron. However, when two baryons or let's say, well, in fact, there are usually baryons present within your nuclei. So yeah, when two baryons, by baryons I mean neutron and proton, interact with each other, then they release a pi meson with one another that contains one up quark and one anti-up quark, perhaps.
Down quark?
No, there was this one quark and one anti-quark. I'm not sure if there were one down anti-quark and one down quark. I will look into my notes
Okay,
for
that's
this.
okay. Okay, so next slide, please.
Yes, ma'am.
Okay. So we talked about the strong nuclear force. We talked about the repulsion. Okay, you go down. Okay, go down further. Okay, now you're talking about the barrier, right? So
I try to give a classical intuition of what is happening in the quantum world.
yeah. So can you give us some other example of barriers that we may have?
Oh, barriers, well, it's not always a hill and a ball.
Yes.
Yeah, it's as I said that we can talk about the gravitational potential of our Earth.
Yes.
If I want to leave this Earth, I need to have energy of this particular amount that the velocity with which I leave Earth should be greater than my escape velocity.
Mm-hmm.
All right? But it can, well, and classically speaking, it can never happen if my velocity is less than the escape velocity of Earth's gravitational potential energy, or Earth's gravitational potential. I would never escape the planet, classically.
Mm-hmm.
But quantum realm mixes the rules up a bit. That's why we call it the non-intuitive side of physics.
Do you think non-intuitive would be the right word?
Yes, it would be, because if, let's say I am standing over here, you're only seeing one muscle. I am extremely localized at one point, showing particle behavior, or at least a system of particles. You cannot see me over here or over here. As I said in the presentation, according to quantum mechanics, there is an infinitesimal chance that I might be on the moon.
So it's a probability, right?
Yeah.
Okay, so when I say example of a barrier, you talk about the gravitational potential, right?
Yeah, and that regular hill kind of a barrier.
Yeah, okay.
And now there is another application of quantum tunneling too, and that includes the transistors of the laptop that you're using.
Electronics, yes. So we talk about a potential barrier there
Yes.
as well. Yes, of course. And then you can apply it to other things like solar cells
Yes,
and so.
ma'am,
So these
exactly.
have many. It's not just an abstract field. It has very practical applications, right?
Yes.
Okay, great. And opposite to the potential barrier, what's the opposite concept of potential barrier?
An opposite concept of a potential barrier?
Of
Quantum tunneling.
we have a potential
Yes, ma'am.
barrier,
Yes.
and the opposite would be
Some place having no potential. Ma'am, let me draw a diagram to get the idea of what you are asking.
okay. So normally when we do this in
I'm drawing a regular infinite sphere well. Should I?
yeah, that's what I was talking about.
Okay.
Yeah, right.
Infinite sphere well.
Okay, and the opposite is the rectangle. You know?
Yeah, it's a rectangle.
Yeah, you showed it with a hill, but
Yeah.
normally when we do the derivations, we show it with a rectangle.
I use the rectangle
Yeah,
too.
yeah.
I use the rectangle too. Yeah.
Yeah,
You see, this is the rectangle.
yeah. So a barrier would be a repulsion, right? And a well would be
Something that attracts.
an attraction, right? Good. Okay. So you've given us the concept of probability versus position, right?
Yeah.
And what's the little wave up there?
Well, it was actually defining that this wavefront is what defines the particle.
Okay.
It's just for the reference of it. It doesn't tell us about the particle. It's a key.
Okay, right. And if you come down,
Yes, ma'am.
okay. So this is a very good diagram. In fact,
I do it myself.
seriously?
Yes.
How?
By using MS Paint.
Wow, it's really good.
Thank you.
It's very good. But for I can see it better on my laptop. But for presentation purposes, you should.
Yes, that's why I was asking him to increase the resolution of that.
No, it's not a matter of resolution. You could increase the size of this diagram. I can do it right now if you give me a second. So, but it will not affect what you because we're using different laptops.
Yes.
So, what one thing you should keep in mind whenever you're making a presentation, right? From the presentation point of view, is that maximize the size of the diagrams.
Mhm.
And also you take a reasonable font size because for example okay,
Actually, I thought that we would be using those like big kind of projectors that are installed in our classes. They are very proficient.
okay, you
Like the one we have in S007.
007
Where we usually
the auditorium you mean?
No, where we usually take our classes.
Oh, okay.
That's very
Well,
powerful,
actually-
and you can see each and every detail.
Okay, no, but still I would recommend
Yes, ma'am,
that
I
you
will.
increase the size of this. It's a very good picture, explains a lot, but again, increase the size. Okay, so try to adjust the text in such a way that you can increase the size of your figure, plus especially the labeling of the figures, because if I see here I understand R and R naught and all that, but if I see there I don't understand R and R naught.
Yes,
Okay,
ma'am.
it's too small. And another rule of thumb in case of making a presentation is that your font should not be less than 20.
Right.
20 is the minimum. Always try to go for more than that.
Yes.
So for that case, like I see, this is too small, right? I cannot understand it. But again, it's a very good diagram. I had no idea you made it yourself. So
Ma'am, you motivated me a lot that day when you told me about this doodle.
of
stuff.
course, like it illustrates the concept much better than you can do it with words, right?
Yes, ma'am.
Okay, so did you put this in your paper also, this diagram?
Yes, I did.
Okay, great. So you're talking about R and R naught. R is the radius of your
Of my nuclei.
okay, and
R
R
naught is the point where your energy, where the
okay, either either. It's fine.
And R naught is the point where the energy, the Coulombic potential barrier, height
Yeah.
of Coulombic potential barrier, is equivalent to the energy of the particle that is being emitted out.
Okay, right. Okay, so good. So this is nice. Again, for the derivation, I can see it here, but again, because of the font size, I cannot see it clearly there. And I'm lucky I'm sitting on this laptop. But anyway, Also, how did you write your equations? You've written them very well. Normally,
Thank
it's,
you.
how did you do this?
I wrote them in Word and then copy pasted it over here.
But this is good. Sometimes it's not that good. Sometimes it degrades the.
Yes, ma'am, it always does, but yeah, I had
This
to do
time it
more.
was very good.
Thank you.
So it's very, very nice. So you said this is very similar to Geiger-Nuttall law, and you could have put the law here also, you know, to
Oh,
make
yeah.
a comparison.
Yes, I could.
Yeah, so that could be that could show us what you mean by similarity. Okay, so and again, radioactive alpha decay is possible only because of this. Such processes cannot happen. This go quantum. Wow, so you're a fan of quantum. That's nice.
Yes.
Yeah, this is nice, and this was one of the proofs that gave for the quantum theory, right?
Yes, ma'am.
That the usefulness and the validity of the theory. So it was very interesting
Thank you.
and very well done, and
Thank you so
I appreciate your enthusiasm for this.
I'm
ठीक है?
really glad that
तो
you did.
पूछ लो तुम दुर्गाना, तुमने तो क्वांटम पढ़ी भी हुई है। दुर्गाना मुझे बड़ी थकी हुई लग रही है। Are you tired?
मेरी सुबह से क्लासेस हो रही थी, सुबह से कैंपस 10 बजे से कैंपस में अभी तक कुछ खाया नहीं है, तो
Oh, why?
नाश्ता भी नहीं किया।
क्यों भाई ऐसा क्यों किया? So anyway, it's very nice. Thank you so much. I'm sure the paper would be even better.
Yeah,
Right?
it's almost the same thing that I just told
It will be
you.
more detailed, I suppose.
Yeah, the derivation is very detailed because I think that this is the main thing that matters.
Yeah, and
The
did you also
derivation.
write the explanation of the derivation?
Yeah, along with it,
Yeah.
like I'm substituting this value.
No, but
and that
also
value.
why? What are these symbols and what they mean and what's the physical implication and things like that.
No, I didn't write the physical implications. Was I supposed to?
Well, to give some physical meaning to the equations.
I understood that, but
That's okay. I think it must be good.
thank you.
ठीक है. So thank you very much.
Like my talk had more talking, less maths. My paper was more maths, less talking. I wanted it to be a yin and yang.
Okay, good.
Have you heard of yin and yang though?
I'm not sure now.
It's like this thing that says.
Are you recording?
No मैम अभी नहीं कर
अच्छा
प्रेजेंटेशन रिकॉर्ड की।
अच्छा
So this thing says that lightning is light without darkness has no meaning.
Okay.
Happiness without sorrow has no meaning.
Oh, okay, right. I've
Yeah.
seen that diagram. Yes.
Yeah, and similar, and everything should be in contrast to each other to give it a proper meaning. So what I try to do in my presentation and my paper is that I try to do more talking in my presentation
Huh.
and more maths in my paper. And
Okay.
the same goes for less maths in my presentation.
Yeah,
And-
because people will start sleeping if you put
Yes,
too much.
and if they want something in detail, they can read the paper.
Yes.
The maths and the detail, the thing that is lacking in it. So
Yeah.
I came up with this strategy for
Okay.
this
Yes.
wonderful course.
Okay,
And
that's
now I'm
great.
gonna miss nuclear physics.
No, you don't have to miss it. Actually, this is the beginning.
Yes, it is, but
You have a lot to go further, right?
do that.
Okay, so I am asking the people on Zoom if I'm trying to communicate
Yes, ma'am.
on both sides, if they have a question, but no one has asked anything so far. So should we go forward or should we ask them? ये speaker जो पड़े हैं,
Good for nothing. No one is talking over it.
yeah, you can speak if you want.
They're not attached to your laptop, they're attached to mine.
Yeah, but I can attach it. It's not a problem. But we don't really.
No, ma'am, I have no questions.
ये बोल रहा है शजील। शजील तुम्हारी तबीयत ठीक है?
मैम, no, मैम।
क्या हो गया था?
मैम घर आया था, उसके बाद तबीयत खराब थी, तो अभी उठा हूँ तो सर में काफी दर्द है, तो फिर बस जाग रहा हूँ।
अच्छा, सो तुम अपना प्रॉपर करवाओ चेकअप, हाँ? ठीक है?
Yes, ma'am.
ये इसको असद को हेलो बोलो।
Hi, Asad.
Hello, Sajid.
अच्छा।
It was really good. Actually, I came at the end, but it was really nice.
It's nice. We will upload a recording as well. Okay?
Sure, ma'am.
ठीक है? And Aman, do you have a question?
No, ma'am.
No, ma'am. तुम सो रही थी?
No.
And Zareen?
ma'am.
No, ma'am. Okay, so it's no, no, no. Okay, anyway, I'll upload the recording. You can ask questions then also. Okay? Asad is always available. Right? ठीक है? Okay, so now, thank you, Asad.
Thank you, ma'am.
अच्छा, तुम्हारी recording हम YouTube पे डाल दें?
Yes, ma'am. For
Moodle
sure.
पे डाल
Why
दें?
not?
ठीक है?
Yes, ma'am.
अच्छा, with your permission, right? Okay. So,
Yeah, let me open my
you
email.
can
Okay, Rami.
click
Presentation.
the same link again when this meeting
अभी आपने
ends
मुझे वो FC वाली बताई है,
to
है ना?
rejoin. And
यहाँ पे मुझे नहीं आया।
नहीं मिल रही
Rami?
किस एड्रेस पे भेजूं उसको ये बताओ ना. And
आप बूस्ट पे भेजो ना वो FC कॉलेज वाले पे।
फॉरवर्ड कर दो. जो खुला हुआ है उसी पे फॉरवर्ड कर दो ना.
ठीक है, मैं लिख दूंगा email address.
ओके, सो हम इसको डिस्कनेक्ट करते हैं और दोबारा से कनेक्ट करते हैं. ठीक है?
श्योर मैम.
वाह, शजील बेचारा बहुत ही बीमार हो रहा है. हाँ,
यस मैम, अनफॉर्चुनेटली.
अनफॉर्चुनेटली नहीं, इलाज कराओ अपना, ठीक हो क्या?
यस मैम, पहले भी सही होके रहा था लेकिन मैम फिर से तबीयत खराब है.
चलो.
एक्चुअली मैम मुझे स्पाइसेस खाने की बिल्कुल आदत नहीं है और हॉस्टल में रहा हूँ तो वहाँ का
ओहो,
खाना काफी
खाने का
स्पाइसी होता
मसला
था
था तुम्हारा?
तो इस वजह से.
नहीं,
यस मैम.
there are options, we could talk about them. There are options where you can get healthy food according to your requirements delivered to you. There are such a, huh?
Eat Subway every
No,
day.
please. No, you can get home cooked food according to your requirements delivered to your place. Okay? आइंदा ऐसा ट्राई करके देखना.
बहुत अच्छा होता है सब.
शजील की मीटिंग